extensive program of research and development in the field of disc flight, which was started in 1952, is being conducted by Avro Aircraft Limited at Malton, Ontario. Early studies on behalf of the United States Air Force proved the feasibility of a circular planform vertical takeoff aircraft utilizing a system of peripheral jets for propulsion, stabilization, and control. The current phase of the program entails the design and construction of the Avrocar, an 18-foot diameter test vehicle for the United States Army. The Avrocar will take off vertically and carry a useful load of over 1 ton for 125 miles. It is intended primarily for operation within 400 feet of the ground over terrain of not more than 10,000 feet altitude at level flight speeds up to 225 knots. When the basic design criteria for the vehicle were established, construction of a full-scale wooden mock-up was started. Radially disposed ribs with covering skin form the primary structure. Unlike the actual vehicle, which is manufactured in 3 segments, the mock-up was built in 2 halves. A covered superstructure of beams and partitions form compartments for the crew, power plant, equipment, and cargo. The vehicle is powered by 3 Continental J69 engines driving a turborotor located in a central air inlet. The turborotor expels air through ducts formed by the ribs and skins to a nozzle at the wing periphery for propulsion and control. A separate fuel tank is installed for each engine. Exhaust gases from the engines, which act as gas generators, are directed through tusk-shaped ducts onto the turbine section in the turborotor. As detailed design information became available, the installation of systems and equipment progressed. The completed mock-up provided a dimensionally accurate and fully representative model for evaluation prior to construction of the first Avrocar. During manufacture of the first vehicle, the mock-up continued to provide an invaluable check on the arrangement, location, and clearances for various installations. A 1/20th scale model designed and manufactured for use in the Avro ejector wind tunnel provided preliminary data on the aerodynamic characteristics of the Avrocar, both in hovering and in forward flight. To provide more detailed aerodynamic data, a 1/5 scale model of the Avrocar was designed and constructed for testing in the Massey Memorial Wind Tunnel at Wright Air Development Center. Before being dispatched to WADC for installation in the tunnel, the model and its supporting structure, together with integral force balance, were assembled. Tests were carried out to check the functional behavior of the model and the balance. Wind tunnel tests, including flow visualization tests, were performed to determine aerodynamic characteristics and pressure distribution during takeoff, hovering, transition, and forward flight. To investigate the unique system of propulsion and control to be used in the Avrocar, a full-scale 20-degree segment of the peripheral nozzle and outer portion of the wing was constructed. tests were performed at the Orenda Engines test establishment at Nobel. Here, airflows and pressures could be provided to the segment to match those supplied by the turborotor in the actual vehicle. Two spoiler rings in the throat of the peripheral nozzle deflect the jet flow for pitch and roll control. Instrumentation was installed to supply data to automatic recorders and manometer boards in the control room. Vertical takeoff and hovering are achieved by downward deflection of the peripheral jet, which in the proximity of the ground produces appreciable thrust augmentation. Transition from hovering to forward flight is achieved by rearward deflection of the jet. This hovering model was built to investigate the system of stabilization used in the Avrocar. An electrically driven gyro in the center of the model simulates the turborotor and operates gates controlling the emission of air at each tip of the cruciform. Because the center of gravity of the Avrocar is located approximately in the center of the circular planform, stabilization in pitch and roll is required. On the vehicle, the gyroscopic characteristic of the turborotor is used to sense the rate of imbalance in pitch and roll and introduce corrective bias into the flight control system. Later in the program, the 1/20th scale model was modified to provide vertical damping data. This information, together with results from previous tests, was used in conjunction with a simulation study being performed on an electronic analog computer. The analog computer was operated as a flight simulator with representative controls and instrumentation. Response of the airplane to disturbances of varying magnitudes and frequencies, together with coupling characteristics between the turborotor, pilot, and spoilers, and the ensuing effect on handling was investigated. From this, the most satisfactory control system parameters were determined. With the release of drawings of the main structural components, planning and tooling for manufacture of the test vehicle began. The circular planform resulted in an economical tooling program requiring only 10 subassembly jigs and permitting the use of many identical parts. One final assembly jig is used for assembly of the main structural components. Manufacture of the 1,700 different detail parts required for assembly of the major structural components of the vehicle commenced in a security-guarded area where the vehicle was to be built. The basic structure of the Avrocar comprises a center base around which 3 identical wing segments are assembled to form the circular planform. The wing segments are separately fabricated from radial ribs and upper and lower skins. Ducts form between the ribs provide for the passage of air from the centrally located turborotor to the peripheral nozzle. Together with the center base and 3 additional ribs, the wing segments are married up in a final assembly jig. Engine air inlet ducts, each centrally divided by one of the 3 additional ribs, are formed between the wing segments on final assembly. The outboard end of each of these ribs is reinforced to carry a landing gear leg. As assembly of the primary structure of the first vehicle neared completion, manufacture of detailed parts and major structural components for a second vehicle advanced rapidly. After assembly of the primary structure and the installation of the tricycle landing gear, the vehicle is removed from the final assembly jig. Three transverse beams enclose the turborotor, engines, and fuel tanks within a central triangular compartment. Each engine is installed in a separate bay, and fuel is supplied by three independent fuel systems. Crew and cargo compartments are located outboard of the transverse beams. The turborotor, which is a turbine compressor combination, was developed by Orenda Engines Limited. To achieve a lightweight unit, hollow brazed steel compressor blades are used. In this pilot program, one blade was processed to prove the suitability of the copper brazing employed in manufacture. The two compressor blade segments, a root fitting and a tip fitting, are installed in a jig. Flux is then applied prior to installation in a bell for brazing. The compound shaft on which the turborotor is mounted incorporates a bearing between the inner and outer components which permits the turborotor to topple fractionally. This motion is transmitted to the spoiler rings in the peripheral nozzle. Radiating from the hub of the turborotor, the 31 compressor blades terminate in fittings to which 31 turbine segments are attached. Each turbine segment incorporates 4 blades. A simulated inner wing with integral anti-swirl vanes was manufactured for the purpose of testing the turborotor. The turbine nozzle ring and turborotor casing were introduced to simulate as closely as possible the conditions under which the turborotor would operate in the vehicle. The completed turborotor was then installed. Finally, it was checked in readiness for the extensive ground test program. The entire assembly was mounted in the turborotor test rig, and the tusk-shaped exhaust ducts used in the vehicle were fitted. To simulate the power provided by the 3 Continental engines, part of the output from one Orenda turbojet was ducted to the test rig.
Given Mark 3, that's 36210, 1420. 11.3, 12.3. Lateral, 5 mil. Vertical, 1.5.
150 hours of testing were accomplished satisfactorily on the first turbo rotor. Subsequently, a second turbo rotor, which had been proof tested for 8½ hours, was installed in the vehicle. The turbo rotor casing with turbine nozzle ring was then positioned. The third engine and its associated exhaust duct was installed. Attachment of the turbo rotor air inlet fairing followed. During construction, numerous tests were carried out on the various airplane systems. Typical of these were control system checks. Installation of the inner wingtip permitted mechanical checking of the transition control rings. The rings are used to direct air during hovering and transitional flight. After attachment of the outer wingtip, a final check is made of operating clearances. Similar tests were conducted on the spoiler rings and yaw control vanes in the throat of the peripheral nozzle. Fitting of canopies and hatches brought manufacture of the first Avrocar to completion. The vehicle was weighed, and estimated values of weight and balance were confirmed. After weighing, the Avrocar was moved from manufacturing into the test area. This marked the end of the first part of the contract, some 2 months ahead of schedule. In the test area, equipment will be installed in the vehicle in preparation for the ground test program. Successful completion of ground tests will enable flight testing to commence and provide information required for development of the Avrocar.